Okay, so we want to perform these three steps. We said that steps 1 and steps 3 are fairly easy, but it's step 2 that's rather hard. So to simplify step 2, we're going to study a toy model in which we can see all of the features that we expect from step 2. So let's introduce now the toy model version of step 2. Now, if you guys remember, when we were introducing Feynman diagrams, we started off with a toy model, and that consisted of going to 0 dimensions. I'm going to use exactly the same kind of a strategy here. In 0 dimensions, I'm going to have one field that I'm going to call the low energy mode, and one field that I'm going to call the high energy mode. But it's a purely naught dimensional theory. So here we go. I want to calculate some correlators, phi less than, so some power of phi less than. This will be equal to, now we'll have a normal integral over phi less than and a normal integral over phi greater than. So in this toy model, we only have two modes. One of them we're calling a low energy mode, and one of them we're calling a high energy mode. Good. So that's what our correlator would be. Now we need to say, what is the action? Well, the action would be 1/2 phi less than squared plus 1/2 phi greater than squared. So there are the quadratic terms for the two fields. And then we'll introduce a vertex with coupling strength G, and there'll be a phi less than squared field and a phi greater than squared field. Good. So what are the Feynman rules? So here are the Feynman rules of this theory. So let's first of all not even think about integrating anything out. If I was just going to study this theory with the two modes, what would the Feynman rules be? Well, I'd have one rule for the first term in the action, okay? And this would be for a low energy mode, a low energy mode. And you can work out exactly what that rule would be. Actually, I think with the choice that I've made for alpha, that rule would just be 1. Then we would also have this over here. This would now be a propagator for the high energy mode. And then finally, we would have a rule for this interaction, and this would be the vertex, okay? And what does the rule for the vertex look like? Well, we would have two low energy legs and two high energy legs. So still a quartic field. And the rule for this, we would have a minus G and then some combinatoric factors that I'm not going to worry about. But the vertex would come with a minus G, and this is the level of precision that I want. I don't really want any more precision than that. There is an observation that I want to make about this action. If you look at the action, so S has a symmetry, and the symmetry that it has is you can change the low energy field into minus the low energy field, and the action doesn't change. Of course, that symmetry is also there for the high energy mode, but I'm specifically pointing it out for the low energy mode because that will have some implications for the theory that we obtained after we've integrated out the high energy mode. Good. Okay. So that's the symmetry that S has. So now let's try to calculate the effective action. E to the minus S effective. What does this look like? Well, it will be an integral from minus infinity to infinity of the high energy mode, and we should have E to the minus S. Okay. The nice thing about this toy model is that we can do this integral exactly. So let's see why. So we've got an integral from minus infinity to infinity, d phi, the greater than mode. And then we've got e to the minus 1/2. We've got the less than mode squared. And we've got minus 1/2. We've got the phi greater than mode squared. And then we've got 1 from the red terms. But then we've also got plus g phi less than squared, and that's from the green terms. And what you see is this action only depends on phi greater than squared. Because it only depends on phi greater than squared, this means it is in fact a Gaussian integral. So we can write down the answer immediately. This is 2 pi into 1 plus g phi less than squared. And this should be square rooted. Great. And then we've got e to the minus 1/2 phi less than squared, because because that term just didn't participate in the integral at all. So I can rewrite this in the form of an effective action. So we've got e to the minus 1/2 phi less than squared. Then we've got plus the log of the square root of 2 pi. So that's just a constant. But then we've got minus, let me put a half here because we're taking the log of a square root. And it'll be the log of 1 plus gx less than squared. And I can very easily expand this log and get a nice series expansion for the effective action. So this is what the effective action looks like. We've got 1/2. Oh, sorry. Let me just correct this notation. That's phi less than squared. Okay, good. Okay. So we've got 1/2 phi less than squared. Okay. And then we've got minus 1/2 times the log of 2 pi. So that's just a constant, not too important. And then we've got a sum. So we've got minus a sum from n is equal to 1 to infinity. So there's an infinite expansion of that log. We've got minus 1 to the n. The denominator is 2n, the 2 coming from the 1/2. Then we've got g to the power of n, and we've got phi less than to the power of 2n. So if we were looking at the Feynman rules for the effective theory, so what do those look like? So Feynman rules for the effective theory. Okay, so let's just discuss this. So I'm going to treat this second sum that's appearing over here as perturbation, since they all come multiplied by powers of g. So from this term over here, we've got a propagator for the less than mode. Okay, so this is the propagator of the low energy mode. So in fact, sorry, let me just change this because I want to keep the same color scheme that I had before. So I'm going to make that blue. And this, I think before we were using interactions, I used a green. So this will be the vertices. Okay, so this will be for the vertices. And then what are the Feynman rules? So we've got this for the propagator of the low energy mode. Good, so that we've still got. Then we've got this constant, minus 1/2 log 2 pi. You could interpret that as the vacuum fluctuation, the vacuum energy of the high energy mode. But then take a look at the vertices. There are many, many different vertices. So with the term from n is equal to 1, so let's just see what that gives us. So there's a phi squared there. So this interaction vertex will have 2 legs, and it will come with the rule of minus g. I'm not worrying about factors. I just want to see what kind of vertices appear. Then when n is equal to 2, the strength of this will be g squared. And in fact, I will have a quartic interaction. When n is equal to 3, let's not skip out 3. When n is equal to 3, the strength would be minus g cubed, and I would have 6 legs on this vertex. And it keeps going. N in the sum runs all the way up to infinity. So we have generated an infinite number of vertices. So one thing you might ask is, why is S effective, so complicated. All of a sudden, an infinite number of vertices, whereas previously we only had a finite number. Well, I want to show you. Let's take a look at what kind of diagrams we would have had in the original theory. And then let's see what we would have had in the effective theory. Okay, so we'll just compare the two. The effective theory should be reproducing the original theory. So let's see if we can see how that happens. Well, we do have a Feynman rule for the low energy mode in the original theory and one in the effective theory. So that matches, so no problem. Now, take a look. In the original theory, we had propagators for both the low energy mode and the high energy mode, but we also had this vertex. So let's start using that vertex. So what we could have had, we could have this. This is one possible diagram in the original theory. And we could have had the high energy mode propagating in the loop. Because we've got a single vertex, this would have come with a minus g. In the effective theory, what we find is we do have a vertex with two legs and it comes with a minus g. Okay, that was the first vertex that we found. So in fact, this interaction, this effect in the original theory that involves a high energy mode, you can see that red loop there, has become just a single vertex in the effective theory. So the effective theory invented a vertex to take into account that interaction of the high energy modes. Then we could also have the following. We could have a diagram like this in the original theory. Okay. And what would that correspond to? This would have a coupling strength of g squared, because there's a minus g times a minus g, that's just a g squared. But in the effective theory, we have a quartic interaction, and that has a strength of g squared. Let's do one more. In the original theory, we could have imagined this Feynman diagram, okay? So there we go. Now, because there's three vertices here, this would have come with a minus g cubed. And in the effective theory, we indeed have a 6-point vertex, and this indeed comes with a minus g cubed. Okay, so what we see in the original theory, we had two fields and only one kind of a vertex that allowed the two fields to interact. In the effective theory, we are inventing more and more vertices, and these are just invented to take into account what the interactions that would have been generated by exchanging the high energy modes. So maybe as a bit of a summary, over here we can say we have one vertex, but two fields. That's in the original theory. In the effective theory, we have one field and an infinite number of vertices which are supplying the interactions mediated by phi greater than. So that phi greater than field, that red field, can propagate in the loops and induce interactions amongst the low energy fields. And the effective theory has generated all of those vertices. Is there a pattern that we see? Well, yes. You can see that if you take a look at the action, only even powers of phi less than appear. And why is it only even powers? Well, that's because of the symmetry that the action had. This symmetry that we could shift phi less than into minus phi less than, that symmetry survives, and we only have even powers. So only even powers, and this is due to symmetry. Okay, and great. all of these points that we mentioned here will hold in D dimensions. So let's just summarize our conclusions, because our toy model has taught us essentially everything that happens in step 2. So first consequence is that step 2 generates new terms in S effective. So it generates all kinds of new interactions. Next, every term consistent with the symmetries of the theory is generated. So the symmetries play a big role in telling you what terms you can have in the effective action, and then all possible terms are generated. Now, what happens at very weak coupling? So at weak coupling, well, at weak coupling, if you were acting just to the leading order, you would say, well, S is just 1/2 phi less than squared plus order G. And if you were saying, well, I want to be slightly more accurate, then you might say S is equal to 1/2 phi less than squared. And then you might add in the first term coming here. So when n was equal to 1, we would get plus 1/2 G phi squared. So you might add that term, plus 1/2 G phi less than squared, plus order G squared. Or you might have included a few other terms. But the point is, if you're at very weak coupling, step 2 does not produce a lot of changes. Of course, if you work exactly, then it produces an infinite sequence of vertices, as we've seen. But at weak coupling, step 2 does not modify S a lot. Good. Okay, so that's the discussion of step 2. I hope that you now have some intuition for what step 2 does. In the notes, you'll see that I've also given a discussion in 3+1 dimensions. I did that mainly for completeness. I think the discussion that I've given you now, which was not in the notes, really is the correct way to think about step 2. And I think that you don't need anything except for this intuition when thinking about step 2. Okay, let's move on.